time, feel free. We'll get that sent out to you ASAP. So without further ado, I'll hand it off to Denny, and Brock's gonna come over and switch chairs with me.
Hi, everybody. My name is thanks very much, Karen. My name is Denny Lee. I'm a developer advocate here at Databricks, based out of Seattle, Washington. So that's why I'm actually sitting with a very weird espresso background while Burak moves chairs and pops on over. He's based out of San Francisco, California. So without ado, you currently are watching our interview with Burak for the genesis of Delta Lake. But before we go into it, the heart of this type of online meetup is that we get to interview the people behind the technology. So Burak, why don't we start with you and you tell us a little bit about yourself.
Yeah, hi, Denny. So hello, everyone. My name is Burak. I'm a software engineer here at Databricks. I'm also a Spark committer. Basically, I work in a team called the Stream Team at Databricks, and our goal is to make the lives of data engineers much simpler. And our team motto is, we make your streams come true.
That's right. The old purple t-shirts that say that the stream, make your streams come true.
Yeah.
By any chance, did you make up that phrase or somebody else did in that case?
I mean, I don't know. We were joking about it. Like we had like versions of "May your streams come true," "We make your streams come true." It kind of like we were joking around. Like we called ourselves the Stream Team, or like once we started working on Delta, we like switched it off to like Dream Team and whatever. It was kind of like just joking around.
Right. So the standard rigmarole of geeks trying to think of marketing phrases. Got it.
Exactly.
Right. So, let's go backwards a little bit though. Can you tell us how you even progressed? Like what made you decide to even get into computer science or engineering? What's your background? I'm just curious here.
Yeah. So I'm originally a mechanical engineer, but I've been programming myself since like high school, early high school. I was like really interested in robots and kind of like bionic arms and things like that. So it's like I wanted to get like a full view of like engineering, where, you know, mechanical engineering, you build, you know, things that move, work, you know, control systems. And on the other hand, like you have to program them. And I really enjoyed that whole area of, you know, like making something work, making something move, and everything. So studied mechanical engineering, but then came to the US, did something called management science and engineering, which is kind of like industrial engineering. So worked on large scale optimization problems. And that's how I kind of got into the world of big data.
Cool. So you finish your degree in mechanical engineer, then decide to switch gears, go into the management aspect, right?
Mm-hmm.
So that was big data. Where did you go to school, right? You notice that a lot of the folks are Berkeley based, but I don't believe you're Berkeley in this case.
Yeah, I did my, so I came to Stanford University for grad school. That's where I did management science and engineering. And I was planning on doing like a full PhD program, like 4 or 6 years, kind of like learn everything about, you know, optimization and things like that. But then, you know, that kind of introduced me to the world of big data and machine learning, because, you know, every machine learning algorithm in the end uses some optimization algorithm and some optimization routine to actually get a result. So that's how I kind of got introduced to Databricks and Spark as well.
Okay, so before you got introduced to Spark, because as you noted, you're a committer of Spark, I'm just curious, did you, like, what were the type of libraries or machine learning that you were doing? Was it like, you know, old school Java Mallet? Was it like pre-Python, or were you using Python pandas? Just curious in terms of your progression into the machine learning cycles before then you actually switch over to the data engineering cycles.
Yeah, I mean, honestly, like we were doing very academic research in that sense. Like we had a lot of code in MATLAB, we had a lot of code in C, we had like some code in Java. We were doing like pretty, like, I mean, well-known optimization routines like a stochastic gradient descent. Mm-hmm. And it turned out like I was using like all these tools that, you know, people had built on top of like C or Fortran even. Right. Where, you know, you have the very optimized like matrix multiplication routines and whatnot. So that's what I was used to. I wasn't used like things like, you know, PyTorch or, you know, those kinds of like more modern, you know, machine learning libraries didn't exist.
Gotcha. So we're going back to almost old school Fortran 77 type stuff.
Yeah.
Got it. Okay, cool. No, fair enough. That's even what I did in the past. So completely get you. So okay, so then you finished off your degree at Stanford, but then how did you progress into Databricks? And for that matter, how did you even progress into Spark in the first place?
Yeah. So that, that's like a very long story for happy hour, to be
Okay,
honest.
fair enough.
But basically, it turned out that I was continuing the research of the maintainer of MLlib, Shangri Meng, at
Okay.
Databricks. And I just like signed up for a Spark workshop, which was being held at Stanford at the time. And actually went to a separate interview for a different company that day and missed the entire Spark workshop, but received an email later saying that, oh, do you want to intern at Databricks? I'm like, yeah, sure. And I noticed the email of Shangri, and then I just like sent my resume over.
Cool. All right. So very not the most direct path, but that's pretty cool.
Yeah.
All right. So then now you're a part of Databricks. You started. I believe you had started off saying that you had more focused on the Spark side of things, or did you more focus on the machine learning side of things when you first joined?
And when I first joined, it was kind of like building the tool. So I started off as an intern. One of the things back then, like Spark 1.0 was just released. And we were trying to build, all these tools to figure out regressions in Spark. Like we were adding all kinds of code to Spark. We just wanted to make sure that we didn't regress in performance. So kind of the first things I worked on was like Spark Perf, which was kind of like this library that allowed us to run benchmarks on Spark, run some like machine learning algorithms that existed during the day on like our data sets and ensure that over time, like we didn't regress in performance. And then moved more towards like linear algebra, kind of work on Spark within MLlib, and then data frames came out, then worked on like the statistics routines within data frames.
Got it. Okay, cool. So basically you started doing the mathematics in essence behind a lot of this in the first place. But then since when data frames came out, then is that when you progressed into more of the stream team early on?
Exactly. So that was around the time like we started adding all these like statistical routines into data frames. And then we created the data team at Databricks. And we were tasked with building a new logging data pipeline. And at that time, we were like, data frames are cool. Maybe we should come up with like streaming data frames as well. And so we were wondering like how that would be, because we had Spark Streaming that had this like dstream API. You had Spark Core, which was RDD API, and then you had Spark SQL, which had data frame APIs. Like, how do we connect all these two or three? Like, are we going to have a dstream of data frames? Are we going to have, like some other concept? So that was kind of like early on, we were thinking about, like it would be super cool to have like streaming data frames, but we didn't know what it was going to look like.
Perfect. So let's hold for that. So basically what you're telling us here is that the progression into the streaming data frames, which we'll talk about shortly, but it was actually started off of the fact that on the Databricks side, can you, without obviously diving into too many details, but can you provide some context of why this was such a big problem, or how the type of problems that you're trying to solve?
Yeah, I mean, so it was a humongous problem. I mean, like early on, we had this like very simple batch data pipeline that took 1 day's worth of data, processed it, put it into nice like table. We need to do something else, and then that's when Databricks decided that, hey, a new college grad should build our new data pipeline, and so we kind of like looked into what the industry standards were at the time, and it was this thing called Lambda architecture. And so we decided to kind of move towards building such a data pipeline at Databricks as well.
Got it. So as you started progressing toward that Lambda architecture, this is where that delineation between the concept of streaming data frames versus batch data frames first started for you and your team?
Yeah, precisely. And like, I mean, the idea was, like we were streaming data, which was like a completely different API, which was in Spark Streaming with dstreams. But then we had our batch processing, which was in data frames. And like managing like two completely different code paths started becoming like a hassle. And we wanted to, like we started thinking about like, how can we unify these, APIs and come up with this like logic where, you wouldn't have to change too much code. You just give us, the transformations that you want to do. And, doing transformations on data frames was like super declarative, super easy. And, it was kind of like SQL-like APIs that people were used to. So we're like, oh, can we, like start doing this in a streaming fashion as well?
Got it. Got it. So then from that progression, because you had all this data and because you want to do a Lambda architecture where basically you're doing batch queries, whether it was machine learning or BI or whatever else that you were doing against that data, but you also needed to look at the data live, right, via streaming, right? And so because you're looking at that data live, you want to be able to use that same declarative nature and batch and apply that to streaming. So that was basically part of the reason why the Spark community itself was saying, hey, we see the experience and we wanted to go ahead and build basically streaming on top of the Spark SQL syntax, using Spark SQL syntax, then versus D streams. I'm presuming that's the progression. How did that communication go with the community? How many others were sort of bugging you about the same problem? I'm just curious.
I mean, like, in the stream team, like we had many ideas, but basically people like Matej Zaharia and Michael Armbrust, they, like butted their heads together and they're like, how can we get this to, work nicely? And then they were like, yeah, we could just like unify this within this API. And then, we started, like talking about it within the developer community as well. And then people were like, yeah, this sounds like a good idea. Like, let's just, make it as reusable as possible. If something's, you can point out the same logic in batch and streaming, it'll make it easier to test your code as well. And so there were like a lot of things where we're like, yeah, if we can just like have this one unified API, then, and all you need to do is like change 2 lines of your code, then it's going to make it so much simpler for people to move from like a batch world to a streaming world as well.
Got it. So right now, up to this point, we've got ourselves now at this point, basically you have your streaming data frames and you have your batch data frames, and you've now successfully built up the Lambda architecture, right? So by building the streaming data frames, by building the streaming data frames and by building the batch data frames, and now you have your Lambda architecture, what were some of the issues that you and your team were running into in that case? Because it seemed like you had a solution, you had the Lambda architecture, that was the popular concept du jour per se. So what were some of the issues that you ran into then?
Oh, there were like so many. It's like I can't begin to count. It was like basically, I mean, we would get alerts like every other day on our like pipelines, like something's failing.
Okay.
And I mean, it was just like a issue with, like working on large scale distributed systems. It's we had many cases where, data would arrive late. We would forget to process that data. We didn't know how far back to look, when new data came in. So we just like said, okay, we expect data to come in within 3 days. So let's just like reprocess our entire data set over like 3 days. And as we were doing all this like streaming work, and also our batch pipeline, the latest data that we wanted to query, it was always very slow. And the reason for that was this concept of small files, having a lot of small files. And the idea there is that, I mean, we were initially up in AWS, working with Amazon S3. And these kinds of like storage systems, like data lakes, as we call them, they're just like key value blob storage systems. They're great for storing insane amounts of data, but they're not great at like telling you what data is there or which version of the data is there. It's like, I mean, it's just very hard to give you, like very consistent semantics. So we would hit like so many issues around Amazon's S3 eventual consistency, where we would write out a file, but before writing out the file, you would have to check that the file's there, just so that you don't overwrite it or write garbage data. And that check would prime a negative cache. You would write the file, you try to read it back, and then you have these issues of, oh, the file doesn't exist. And you're like, well, I just wrote it there. How does it not exist? but those were kind of like, the kind of problems that we had to deal with. Listing all those files were, super expensive because, S3 wasn't just built for like listing things. It's very hard for like those kinds of systems to give you a list of what's there. And then just, reading all those small files, opening so many HTTP connections, that would be super expensive. We would be killed on throughput just trying to, access every single file, open all those connections. So, we had all kinds of like performance issues as well as, correctness issues and like consistency issues.
Got it. Got it. So the heart of the matter, for at least when you were doing the Lambda architecture for log analytics, was that the underlying file system, in this case, the cloud storage system itself, was not reliable.
Mm-hmm.
Right. And so I'm just curious, based on, obviously this was your experience, but then did you see the same thing happen with lots of Databricks customers?
Yeah, I mean, like, so it was, everyone was building the same thing at the time. And we're like, with these like architectures, I mean, it's not that the storage system is unreliable. It's that everyone had to build their own database semantics on top of this storage system. And, people were just used to working with things like MySQL or, like data warehouses. And, these kind of storage systems, they were very easy to deal with. You didn't have to think about a lot of the problems that you might face. But then suddenly when you came into this data lake architecture, which, all our customers also were in, and then you had to deal with all kinds of like, how do I deal about files? Like, can I delete files? How do I optimize my IO patterns with these files? Which file format do I save them in? Which file sizes do I want to have? Like suddenly all these like new problems arise that people had never had to think of as an end user.
Right, right. So that transition from on-premise to the cloud, that transition from single box to distributed systems, the fact that you actually had to deal with a distributed file system, this basically introduced a whole set of issues that, not only you were suffering from, but, in terms of doing the analysis of the data, but many of the Databricks customers themselves were actually going ahead and suffering from.
Yeah, precisely.
Right. And so then saying this, then, sounding a little dorky on my part, this is in essence, the genesis of Delta Lake, right? The problems that you ran into basically was the reason why what ultimately became Delta Lake.
Precisely. I mean, we were like trying to solve all these problems, like in different ways. We would get all kinds of like support tickets saying, oh, my queries are slow, or, like my listing is super slow. Can I make this faster? We were getting all kinds of support tickets around, oh, like two people tried to change the same table at the same time, but then I have this like totally inconsistent garbage state of my table. People would be like, oh, I have duplicate records here. Why do I have duplicate records? Well, you had partial failures. Those were kinds of issues. Then, like with Spark, for example, a lot of things were built with like Hadoop distributed file system in mind, where, the idea there was with an on-prem like HDFS, you could just like write to a temporary location, rename, and then renames are super fast. It's like a, constant time operation. Whereas with, cloud storage systems, it could either be a, very quick rename, or it could be a server-side copy of the entire file. Right. And these kinds of like performance issues, people were, as people were like moving from on-prem to the cloud, they just like had so much trouble, dealing with, all these kinds of like inconsistencies and all these kinds of like performance issues. So that really led to the like we came up with like intermediate solutions.
Yeah, actually, with that, I'd love to actually dive a little bit into that in terms of like some of the intermediate solutions you had to put in place before
Mhm.
we actually had the solution. So just to give a little heads up to the audience here, right? We are going to be talking about the Delta Lake transaction log, which ultimately solves some of these problems. But
Mhm.
before we talk about that, I'd love to, just as you hinted at, Burak,
Mhm.
understand a little bit more. What were some of those intermediate solutions, for example, like deduplication or the consistency for the file systems or things like that? Whichever is your favorite pain in the butts, I guess I'll put it that way.
Yeah.
Yeah.
Yeah. I mean, so for example, with structured streaming, once we released streaming data frames, structured streaming, we came up with this file sync implementation where you could take your data from anywhere, Kafka, Kinesis, Azure Event Hubs, whatever, or files, and then you would store it in some other file storage system. And what this file sync did was that it was actually kind of like the initial implementation of Delta's transaction log. It would write out all the files with unique names. So these unique names ensured that you wouldn't ever hit an eventual consistency problem. You would never hit like a failed task writing out a file, and then a second task that retries. That's a retry writing out the same file. You would just like get new sets of files every time. And once all the files were complete, it would just take the set of files that it wrote and then store it in a manifest file that said, okay, this batch, this micro batch, I wrote all these files. And when Spark would actually query this table, it would directly go to this manifest. It wouldn't have to list any of the directories. It wouldn't have to list anything. This manifest was kind of like the source of truth about which files the Spark had to read to actually have a full view of the table. So that was kind of one of our initial solutions to dealing with avoiding listing and kind of like having an atomic operation where if the write fails, then Spark's not going to read those files. Spark's still going to look at the transaction log to see, or a manifest file to see what's the source of truth. So that was kind of like a very early implementation of what was getting us there.
Got it. So basically, the prior to the transaction log, in essence, you have a manifest file, basically just a file, which
Yeah.
lists all the names.
Yeah.
And because if you have a lot of files, listing the files from S3 became relatively slow. So it was actually faster to read that one manifest file, which
Yeah.
itself contained the list of, let's just say, 25 files,
Yeah.
right? Even though there may have been 50 files due to failures on write, for whatever reason, it would only grab the 25 files that you needed.
Exactly. And it wasn't just a single file. It was actually like a ordered operation. So it was kind of like the first batch wrote these files. The second batch wrote these files. Third batch wrote these files. And suddenly, like once we saw this directory, we would have to read, like 1, 2, 3. We would list that directory and then read all the files within 1, 2, 3, and then answer a query based on the file list generated from those.
Gotcha. So like you noted, this was the precursor to the transaction log. So the idea is then basically you had a file. I'm just curious, was there any discussion on why, for sake of argument, that transaction or so that manifest file would in fact be a file versus, for sake of argument, some other like SQL or NoSQL store or something like that? Were there discussions for that, like from a standpoint of a queuing or an in-memory system instead?
Yeah, no, that's a great question. I mean, so there were with Spark, every time the biggest question is scalability. How can we build something scalable? And also one other thing was, we don't want to depend on external systems, avoid dependence on external systems, because it just adds more, problems onto the users. And so we were like, oh, they're trying to write to a storage system. Why not have this, our source of truth along with, all the data files within the storage system? So it was kind of like, we didn't want to have them set up a connection to, some other database. We didn't want to have them set up, a connection to, some other key value store. It's like we already have permissions. They've set everything up so that the right people can write to that directory or read from that directory. Why not just store all the information that we need, in there? So that was kind of our idea. And anything in memory, we just wanted to avoid as much as possible because it wasn't going to scale.
Got it. Got it. So basically the in-memory part, basically because it couldn't persist, right? There wasn't something that you could basically say, this is my source of truth by that very definition.
Yeah, you don't get fault tolerance in that case either. I mean, like the thing is, it's like the moment your, Spark driver is gone, then you just lose whatever you have about that table.
Got it. Got it. Cool. So that, I mean, that solved basically the manifest file basically did solve a bunch of things, and like especially the file rights issue. But I'm just curious. Then you started off with the Lambda architecture, really talking about streaming, right? So was it just the manifest itself that would solve the streaming issues that you're in the resolution of streaming, or what else did you have to do in order to be able to resolve these things?
Yeah, I mean, so the manifest file kind of like resolve the issues around like distributed failures, partial failures, and like a file listing with streaming, but it didn't get rid of the problems of, like having a lot of small files, because, the manifest is the source of truth. It tells us, like which files we have to read, but then it was only, it only worked with streaming rights. So how do you actually read from this table and like compact your files, at the end of the day? Like, do you have like one table that's just like streaming and then you compact to a separate table, or, do you like ignore, like some customers would just like ignore that transaction log and then just like overwrite everything and like blow everything out at the end of the day, even though like we told them, hey, please don't do it. Like, you're not getting any guarantees this way, but so some people still were okay with that solution. But so, still a lot of issues existed because there was no like unification with batch yet, especially with this new like streaming file sync. So in the end, we noticed all these problems. People were starting to use structured streaming a lot more. And then we're like, well, maybe we should start thinking about this again and come up with this like V2 concept of a streaming, because people don't want to write actually also you have to deal with multiple streams. So we started seeing these like usage patterns which like we couldn't support with the system.
Oh, apologies. There seems to be some connection issue. I'm not sure if it's on my end or on your end, but can you hear me okay, actually? Okay, well, this is, I guess, the love of doing live sessions where sometimes we have technical difficulties. I don't know if it's on my end or your end, but nevertheless. Okay, let's progress, because we actually only have a few minutes left on the interview portion of it, because we did want to try to time these interviews to be timed for about the length of time, for the average length of time it takes for somebody to commute in San Francisco, which is about 32 minutes. So nevertheless, all right, so you've went ahead and told us a little bit about how that transaction log worked, the streaming sync. So then what were some of the other issues that you ran into as well, right? Especially with your customers, in terms of like, because you progressed with the file sync, you progressed with what ultimately turned into a transaction log. What were the other things? Like, for example, I'm presuming one of the problems was as time changed, as time progressed, excuse me, business needs changed. So the schemas of the data had as well changed.
Oh, we caught up.
All right,
can you hear us?
I can hear you now. No problem.
Yeah. It's like your face was like, for a second. So yeah, to repeat your question, it was like, what kind of like business need, came up along with, time that the file sync manifest did not support. Another like big thing that came up was GDPR. All this like issues around like data protection and data privacy, and like the requirement for data subject requests, where people could ask specifically for what is my data, or like, can you update my data, or just delete my data entirely. And people had to build like very complex systems and data pipelines or data architectures to kind of solve those issues. But we're like, normally, you should be able to write an update statement in SQL and be able to update your table. That's what people are generally used to. Or you should be able to write a delete statement on your table and delete all the records for a user. And like, that's what, our users are used to from like on-premise, data warehouses or databases. So we saw this like new, more complex workloads, emerging from, like all these new, requirements around the data world as well. And our transaction log, which only supported streaming rights, was never gonna support those use cases. So we had to come up with this like new protocol that actually was able to understand what changes are being made to the table.
Got it. Got it. So now you actually have expanded the transaction log and understands what change made to the table. What made you decide then that it would have to be a SQL syntax? I mean, because it makes us think about the database world all over again.
Mm-hmm. I mean, it wasn't necessarily just SQL syntax. It was SQL. People were just used to SQL, and it was the easiest thing that people knew across like different roles. And it was kind of like the SQL syntax allowed them to transition a lot easier into this world without having to know any Spark APIs or data frame APIs. Maybe data scientists knew about data frames from like pandas or R, but not necessarily a data analyst who was using BI tools or writing dashboards. But we needed to empower all these people to actually build such things as well when required.
Perfect.
So,
perfect.
yeah.
Cool. Well, then let me end the interview portion of this. We'll basically talk about then what spawned you guys to also think of time travel.
Oh, time travel.
Yeah.
Well, yeah. So it's kind of like when we came up with Delta. I mean, it was kind of like with all the intermediate solutions, Delta was kind of like with its transaction log and its protocol, it solved a lot of support tickets that we would get, honestly, around it would ease a lot of issues. Another thing that another issue that came up was with Delta. We tried to enforce kind of like best practices on users, and what would happen was with Hive, there's this concept of dynamic partition overwrites. What that does is that you have a data set, you try to write it out in overwrite mode. So it's going to overwrite some amount of data, and it overwrites only the partitions that it writes new data to. So the idea was, like it was kind of like a lazy way of saying, like I have this, entire new data set, just like overwrite whatever I need to overwrite with this. So the initial users of Delta who were used to that kind of like mode started overwriting their entire tables, which meant deleting all their data and actually just inserting a very small subset of data. And when they asked like, oh, why did this happen? They would, create a lot of support tickets. Oh, Delta lost all my data. We're like, so here's the history log, and here's the operation that you wrote. And, we have this operation called replace where, which you should have, which you can use to actually guarantee that you're overwriting the right data. So, you're not deleting spurious data, accidentally. But here you go. Here's time travel that'll allow you to actually get whatever data was in a previous version, and you can merge all this data back into your current version. So it kind of like the first the first week we released time travel, actually like 6 or 7 customers saved all the data that they accidentally deleted.
Wow.
Yeah.
So that's pretty cool. So basically, even though time travel is a pretty cool, fun feature,
Yeah.
it was born from the idea that people were not using replace where or using overwrite incorrectly in essence.
Yeah. It was kind of like, I mean, it came from the idea that people make mistakes.
Got it.
And, if there's a way that we can prevent or roll back from those mistakes a lot easily, much easily, then, we should provide that, feature to users. And it was actually just from how the transaction log and the concepts of multi-version concurrency control worked. It was really easy for us to actually go back to the state of a table at any given time. So why not just empower users to actually, if they want to query the differences, do that. If you want to, if you accidentally deleted data, add that back. Just provide all that functionality very easily.
Perfect. Well, okay. Well, this has been an awesome interview. I'm glad you've spent the time with us here for today, Burak, on the genesis of Delta Lake and also telling us a little bit about yourself. It's a really interesting journey that you went from basically mechanical engineering to machine learning to being a hardcore data engineer now. I did want to leave a few minutes to ask some questions before we wrap this up. Why don't we just switch over to the Q&A? Would you like me to ask some of the questions or would you like to do? I'm cool either way, whichever one you prefer.
I mean, please go ahead.
All right, perfect. Well, let's just dive into it. We'll go in order. Through the Delta read stream and write stream, do you not achieve what some people would term as the Kappa architecture in addition to the Lambda architecture style? And I'm going to just start off by saying, to probably lead you to this question, in fact, we are probably going to want to talk about the Delta architecture instead.
Mm-hmm.
So,
yeah, I mean, so kind of this concept of having these two tables and or a streaming workload and a batch workload. What we wanted to do with the Delta architecture was kind of you can stream into your table, you can do all kinds of operations on that table additionally, and that came from the biggest power of Delta, which was ACID transactions, which funnily we didn't get to in this interview yet. But yeah, through this ACID transactions, basically you had all the power to, append new data, delete, existing data, compact existing data without, changing, causing any transaction conflicts and whatnot. So by, what we wanted to do was propose this new architecture style called Delta architecture, where you would incrementally improve the quality of your data. So what that meant was kind of you would have data coming in from this centralized message queue, which has a very short retention period, like Kafka or Kinesis or Azure Event Hubs. You can store maybe 7 days worth of data or 2 weeks of data max. And what we wanted to do was, people don't realize mistakes maybe in that short period of time. You need a longer retention period. So the first step would be to take all that data and store it in cheap storage with, leaving it untouched. And from there, you just you do one more layer of refinement where you actually, okay, take this raw data, let me just parse it out, move it into, nicely clean tables where I have my source of truth for all the events that I need, and and then just add one more layer, just combine all these event sources back again to tables that data analysts can query optimally or very quickly. So there the idea was if you had made a mistake, then you can always go back to your bronze table and reprocess everything all over again. If someone upstream that you don't know creates a new timestamp format and all your timestamps now say you're doing something in 1970, then you could always go back, fix your code, and repopulate everything from a certain period of time or from scratch altogether. So these kinds of operations really And like this architecture really, took off with a lot of our customers because, they understood the pain points of like making, unfixable mistakes. And this architecture kind of gave them the flexibility to actually fix those mistakes.
Right. And so actually you called up a really good point, which again, you're right. We should have brought up a little bit earlier, which is the context of transactions. Why was this concept so important that ultimately led to that creation of that transaction log, or ultimately allowed you to be able to provide the reliability within Delta Lake in the first place?
Yeah. I mean, like the idea was like with a data lake, HDFS or, S3, whatever, you didn't have this concept of, I don't know what I'm changing. Like there was no centralized point where you would have, like, oh, I want to make sure that, if I have two concurrent writers, like doing things to my table, I want to ensure that, they are consistent amongst each other. Like I don't want two people trying to delete the same file or delete the records from the same file and update with new values to it. So, or, like if you're doing compaction, compaction means you're going to have a second copy of the data within the same table. You don't want to break anything that, just was running at the time, a query that was started before you start your compaction process. You needed to give it isolation so that, that query can run for 2 days, 3 days, if it's kind of like a deep learning algorithm, for example. But the next time it runs on a fresh copy of the data, which is actually more compacted, more optimal. So we needed to we wanted to provide those semantics, and the transaction log was one way to do it.
Perfect. Okay, so I actually only want to ask one more question, just because we have a lot of other good questions, but I figured some of them are a little bit more detailed, so it probably takes longer than just a quick Q&A. But I did want to ask the final question, which is, when do we expect the full Hive integration with Delta?
Oh, full Hive integration. That's a great question. So we do have a Hive connector right now that we're hoping that people can try out and help give us feedback. So Delta is an open source project. It's under a repository called Delta.io Delta. We have a GitHub repository called Delta.io connectors. And here we wish to have, like connectors for other kinds of analytics engines where, Hive is one of them, Presto is another, and even Flink. And we do have a Hive connector that you can build and run today. And we would love to have, feedback on it so that we can, fix issues if there are any issues. And like, we just want feedback and like have people try it out.
Perfect. Okay. Well, hey, Burak, thanks very much for this great session. I really appreciate your time. I did want to do a couple things just to do a wrap up. So Karen, I don't know if you're going to do a wrap up, but I'm going to at least want to call out some quick things for wrapping up. Number one is that Burak and myself and a few other members of the stream team, we will be doing a 3-part webinar series called Diving Deep into Delta Lake, where we're going to be talking about the transaction log, how things happen when you do updates, deletes, and schema evolution, which we didn't actually get to talk a little bit much about. So we're going to dive into those details. So please be on the lookout for those sessions because we're going to actually have them in the US, EMEA, and also in Asia time zones as well. For the next Spark Online Meetup, we're planning to actually interview data science extraordinaire from Databricks, Brooke Winnig. So I think that's